Now let's look at our multivariable calculus version of a total differential, it is called. So in the previous little segment I did a brief first term calculus look at a differential. Not a very fancy example, but more of a discussion of some of its aspects that are significant. So here's our definition. And if we have a function, and I'm going to just set this up for two variables, the total differential, the notation for that is df. That's the regular letter D there, and is written more formally this way: the partial derivative with respect to x of the function multiplied by dx, the partial derivative of the function with respect to y multiplied by dy. And if you want a slightly cleaner looking version that doesn't have as many symbols to math blind you, you could write it this way: df equals f with respect to x dx, f with respect to y dy. Now, we do know what partial derivatives are, but maybe it is not as clear what dx and dy represent, and I gave a hint of what df might mean in the previous. So let me just slide my little cover fully off here and slide this up so it's more within view. So as the title calls it a differential, you could think of part of the root of that word is what makes it different, or what is the difference. The differential is a way to measure the difference in a function. It will commonly be called measuring, how much does the function change, or possibly even measuring an error. How good is the approximation? But the key fact here is we're approximating. It's not knowledge of the actual change, it's an approximation. In real life measurements, knowing something exact is basically not possible. We just have a level of accuracy that we know. And this is only one technique for measuring an approximate change or error in the function. There are many others. So this is a simple linear approximation method. So that would be df, and the function f will usually have a meaning. We use the letter f for function in a math class, but we don't use that often outside of the math class. You'll see soon. The actual change in the function, like if we could measure things precisely, infinitely many decimals, that would be delta f. It's almost possible to find this, except for a very simple person-made example. We can find approximations, and we can learn to study those approximations in more advanced courses. So let's look at an example of this total differential. All right, so we're going to hit some familiar shapes here: cylinder and cone. And the idea of our cylinder has a circle, radius r, and it has some height we'll call h. I guess this could be called a right circular cylinder. You recall from earlier in the course, there is a different, more generic definition of cylinder that extends to some other cross-section shapes. I'm using the word cylinder here like we learned it when we were a kid. Cylinder. Now if I have a cone with the exact same height, and that circular base has the same radius, there is a relationship between the volume of these two shapes. Now, my pictures are not drawn very well to scale. That's because I am less consistent than I could be with my hand drawings. But do you recall how to measure the volume of these two shapes? So the volume of a cylinder would be the area of that circular base multiplied by the height. And I can still remember my high school geometry teacher many years ago using a plastic cone and filling it with water 3 times in order to fill up the cylinder as a demonstration, not a proof, but as a demonstration that the volume of the cone is 1/3 the volume of the cylinder. Pi r squared h. And there are multiple methods for proving it. There's some fun ones in calculus where you use rotation of shapes to prove that little volume formula. Now, let's look at this problem that is a function. Volume is a function of 2 variables. And let me just show you what the total differential is for that particular formula. So we're going to dive in on the cone, not the cylinder, because it's just more interesting, isn't it? All right, just slide her up a little bit here. So if volume is equal to 1/3 pi times the radius squared multiplied by height, then dV is equal to the following. The partial derivative of the volume with respect to its radius multiplied by dr plus the partial derivative of the volume with respect to height multiplied by dh. And for this problem, if r is the variable, that's 2/3 pi r to the first times h dr plus, if h is the variable, derivative of h is 1/3 pi r squared dh. So this is what you'd see only in a math book, never outside in the real world. Calculate dV, and you'd call this finished if somehow you got paid to do that for a living. And that's generally not where the pay structure falls in terms of our wages or salary. But let's turn it into an actual problem. Remember first that this is the approximate change or error in volume. It's the approximate change or error in the volume. Well, let's actually use it to measure for a particular problem. What if our cone had a radius of 2 centimeters and our height is supposed to have a height of 6 centimeters, but the method of producing the particular cone, there's a possible error in our radius of 0.1 centimeters, which is 1 millimeter. And the same device that makes that cone, when it makes the height could be off by as much as 0.2 centimeters or 2 millimeters. We're going to define the dr and the dh to be these known possible errors of the accuracy of the machine that builds. So this would be dr and this would be dh. And if you can now look, we actually have r and h and dr and dh, which are all the values to plug in here. That would give us an approximate change in error of the volume. And that's where we're going to take it. So remember, you have this pause button. Use it if you have to. Here we go. I'm going to go ahead and factor something out of our algebra, the 1/3 pi, just to make it easier to read and write this expression. If the radius is 2, we have 2 times 2, and the height is supposed to be 6, and the dr is 0.1, plus r squared would be 2 squared, and dh is 0.2, and oh, that is quite messy and hard to read. 0.2, let's say 2, 4, 24, 2.4, 1/3 pi, 2.4, 4 times 2 is 8, 0.8, that would be 3.2 over 3 times pi is the value of dV. Now, let my brain catch up to my calculation skills and find that I've fallen short in quite a few areas here. For starters, V for volume, there are units of volume in this problem, and they should be, for volume, cubic centimeters. So this should be a measurement in cubic centimeters. If I were really sitting in a science or engineering class and using a simple example like this, my units should have been carried throughout the problem and not just merely at the end. So I allow a little bit of leeway in my calculus classroom for this, but I want to pay homage and respect to the people who are hands into it. You would have units everywhere, and you would keep track of the units, because losing track of the units frequently means design failure. Now, if you don't have a calculator, this is where you're done. Problem ends right here if you don't have a calculator. If you do have a calculator, then you're going to wish your teacher didn't give you one, because there is so much more work to do here if we have a calculator. For starters, I don't know how we do this. Well, let's just do this. If we have a calculator, let me just do a baby step. dV is approximately equal to 3.35 cubic centimeters. But somebody has to tell us how far to round this. We have to know maybe significant figures, or maybe there's some given information where we know, do we go beyond tenths because that's the accuracy of that measurement? I don't know. But this is like serious stuff if you're engineering designing, to actually know the number of significant figures. I just chose to round it to the nearest hundredth. But you don't just do that. Somebody provides some guidance there, and sometimes the nature of the problem provides that guidance. Maybe there should be some more zeros after this one to indicate that the machine is really that precise. I don't know. So there's something you can do with the calculator. But here's the next thing. The number pi, it needs a calculator by itself. It's been rounded off, so that makes it a little bit less than perfect. Now, if you went back and actually calculated the volume, 1/3 pi r squared h, and you let your radius become 2.1 and your height centimeters, and your height equals 6.2 centimeters, because those are the possible errors. You could use this to figure out what delta V equals, the actual change or error. Or, so that's a side question you could ask. Or you could look at what's called the percent error, where you look at the dV calculation divided by the actual volume, and to see what that percentage might be. But all of these things would be if you were going to add a calculator at the end. And I'm not going to focus on that in this video because it's already too long. But I want to point out, if your instructor says you don't get a calculator, then you could have retired right here if you're going to be a student and not a real world thinker. But for the real world thinkers, this is just the beginning of analysis. Analysis of accuracy goes way beyond the total differential. And I do have another video for a total differential example, but you should know that this concept of numerical analysis it's some fun stuff. So I encourage you to keep studying. So until next time, see you later.